Hi, I'm Chloe Washabaugh. I'm a co-captain of the Cornell speech team, and here is my info speech on the quantum internet. In 1969, researchers at UCLA typed the letter L into a computer terminal and hit send. They called up their buddies at Stanford. Did you get it? Yes? Great. Okay, next letter. O. Did you get that one? Yes, great. Okay, next letter, G. Did you get that? The system crashed. That was the beginning of the classical internet. The transmission of data from one point to another, as described by Dr. Stephanie Warner to Quantum Magazine on September 25, 2019, is a set of complex and chaotic processes that span data servers and fiber optic cables around the globe. But Dr. Warner and her team stand at a stimulating frontier of science, transmuting the classical internet to behave by the laws of quantum physics. Her research is ushering in a new era of communication, one where we transmit quantum information on a quantum internet. Quantum information is entirely unlike the zeros and ones that form the backbone of the internet I'm using right now. Dr. David L. Schwam on UChicago's Big Brain podcast on September 7, 2020, describes the difference as being between black and white and color. On July 23, 2020, the United States Department of Energy announced its Quantum Internet Blueprint, a plan to streamline the development of a prototype quantum internet within a decade. With billions of dollars of investments by China, Japan, South Korea, the EU, and a whole host of private investors, the quantum internet may be on the horizon. So, at hazard of saying the word quantum 51 times, let's engage with science and learn the physics, applications, and implications of the quantum internet. The idea of a quantum internet was born into scientific canon back in 1935 with the publication of the Einstein-Podolsky-Rosen paper. The idea was to harness the distinct physical properties of atoms, electrons, and photons to hold information. Since quantum physics is abstract, we'll just understand why quantum information is different from normal or classical information. And second, why the quantum internet doesn't exist yet. First, what is quantum information? Classical information exists as a binary bit. Something is either there or it isn't, and that's coded into zeros and ones. But some systems, like a tiny bit of matter, can encode information in a spectrum between 0 and 1. What's actually measured is a probability that's dependent on that distribution. For example, a burst of light, a photon, can be polarized in any direction. Think sunglasses. What's actually measured is how much the light is polarized in one specific direction. In a quantum system, the information is the spectrum itself. Such a system is called a quantum bit or a qubit, and CNBC of April 7, 2020 explains the advantage. Learn to calculate with decimals instead of just whole numbers. Qubits represent a whole new language altogether, and quantum devices are fluent in nature's native tongue. Qubits employ the language of the universe. Second, qubits are notoriously fragile. On the aforementioned podcast, Dr. David L. Schwam cautions that the act of looking at the signal in the cable destroys the message itself. Just like the classical internet, the quantum internet will exist on a series of fiber optic cables connecting data servers. However, over time and space in those cables, a signal degrades to random noise. It dies. Quantum information must be amplified every few kilometers in order for it to reach its destination. The technology to do so, without looking at, measuring, and therefore destroying the message, is called a quantum repeater, and it's an active area of research. That's science speak for it doesn't exist yet. And they said we would have flying cars by 2001. Even when the necessary components are developed, you're not going to have a quantum internet hookup at home. That's because quantum internet is best at solving specific classes of problems. Let's look at two of the earliest adopters: data security and modeling. First, on a quantum internet, the faithful transmission of sensitive data is guaranteed by the laws of physics. According to the Scientific American on September 21st, 2019, a pair of qubits can be entangled, meaning that if you were to separate them by a very large distance and measure one, that measurement automatically appears on the other. Einstein called it spooky action at a distance. When leveraged in a seminal protocol known as quantum key distribution, entanglement allows banks and governments to not only send data with perfect data security, but also know when a third party is trying to listen in because they look at, measure, and destroy the message. Unlike the humans who operate it, the quantum internet is virtually unhackable. Second, modeling and optimization. Quantum computers have verifiably surpassed the computational ability of classical computers, but they don't scale. Harvard professor Michael Lukin in 2019 cautions that quantum computers will likely only ever have a few hundred qubits, but networking them together in a quantum internet exponentially increases their ability to run complex simulations that provide solutions to, say, climate change. The Boston Consulting Group on January 4th, 2020 explains the quantum advantage when it comes to medium-term climate action, discovering new catalysts for carbon capture, optimizing energy-efficient transportation routes, and uncovering novel construction materials. The quantum internet can realize and predict what our future will look like. The footprints of the quantum internet can already be seen around the globe. Underneath the Chicago suburbs lays Argonne Laboratories' 52-mile quantum loop. In Europe, the Quantum Internet Alliance spans 8 countries. Let's look at some implications. First, the commercialization of quantum technology. According to a 2018 Pan Informatics report, approximately 76% of all the academic patent families published in the field of quantum applications since 2012 have been from Chinese universities, severely outpacing the United States. China's billions of dollars of investment in what amounts to perfect data security is identified by the Brookings Institution as being part of a larger scientific drama. By dominating patenting rights, China not only ensures a commercial advantage, but shuts out any hope of substantial scientific collaboration. Because with every technological revolution before it, the person who makes the most money is the one that got to set the standards. Second, geopolitical rivalries are exacerbated by the quantum internet. Since the necessary technology is still highly experimental, the MIT Technology Review of January 4, 2020 proposes a shortcut, arguing that we should put part of the quantum internet in space. Satellites could serve as low-loss waypoints to beam information around the globe with lasers. But Wired of April 22, 2020 observes that while some countries have already put up dedicated satellites for their quantum experiments, NASA is just now entering negotiations to retrofit a communications module on the International Space Station for theirs. Quantum technology is the 21st century's Space race. Like any good researcher, I ought to declare my conflicts of interest. Investment in the quantum internet and quantum technology is my job security. But after learning the physics of the quantum internet, some of its applications and implications, we can embrace a new age of technology that harnesses the laws of nature themselves. Let's watch the quantum internet come into being, one experiment at a time.